Okay, so here's contains. This is just the binary search. We've already seen this. Contains returns a Boolean. We have a binary search. It takes an element and a root. If it returns not null, it's contained, right? This is kind of like doing like that index of thing, right? Remember we had that private index of that would return like, maybe it wasn't index of, find. It was a private find that would return a sentinel value. Well, here the sentinel value, I guess, is null. Whatever. Just basically, if contains returns something, it's there. There we go. Returns a Boolean. Binary search is a recursive one. This is another kind of example of like having a public-facing method that calls a recursive one. Here it has a different name, but whatever. And then here's the private binary search. What does it look like? Well, if current is null, return null. Basically, if we do a binary search and we get to where something should be, and if nothing is there, it's not there, right? Is that clear? I'll do a very simple example. 10, 5, 7, right? If I'm looking for the number 6, where should it be? Well, 6 is less than 10, it should be over here. It's more than 5, it should be over here. No. If I go to where it should be, and it's not there, yeah. Because it's a 17, obviously. Right? You're like 6 should be there. Yeah, well, okay. Because it was, I don't know, big mistake. I know that was a bad one.
You're testing us.
Yeah, totally. So if I go to where 6 should be, if I go to where the thing I'm looking for ought to be, and it's not there, it's not there. Because it can't be anywhere else. So that's the idea. If we ever get down to a node that's non-existent, we haven't found it. Otherwise, let's do our comparison. I'm doing it up here and then storing it into a variable. If you're looking at this and you don't like it like this, you're like, why not just do that in like the if statements, right? Yeah, fine. I don't know. I just kind of like calling it once and saving the result, but whatever. Yeah?
Is there a reason you're comparing it like that instead of checking it with equals for this case in particular?
No, because compared to if it's 0 will be the same as equals.
That's true, and you need to use it later.
And I do need to use it later, but if I did do it with equals, yeah, okay, sure. Yeah. Why not? Yeah. So I get the comparison. If the comparison is 0, then I found it, right? Because remember, current and element, the compared to gives us 0 if they are equal. If they are equal, I'm looking at a node. Like if I'm looking for 5, no. Hey, found it. Done. What do? I return current, the node, referencing the data, a node that contains the data that we want. Otherwise, if comparison is greater than, if current is bigger than the thing that I'm looking for, it must be to the left. So I do the binary search on the left. Otherwise, do it on the right. That's it. That's it. Cool. So that's the binary search. We've already seen this, though, of course. So see the above method called, yeah, okay, count. Count, okay. Well, if it's empty, return 0. So we have a public-facing count. If it's empty, return 0. To be clear, count returns the number of occurrences of a given element. So if I was looking for like, right? I know you can't see half of it, but there's just a bunch of 5s, right? If I was looking for 5, I want to go and return 1, 2, 3, 4. Okay? Yeah. You sure?
It's just a binary search, but with a count.
That's literally it, except we don't stop once we found it. We have to keep looking, right? So it is a binary search, and we go add 1, but keep looking. But where do I keep looking? To the right, because duplicates went to the right. I could have put duplicates to the left, and if I did, then I'd do it the other way. But, yeah. But here's another point to put in there. These are all implementation details. If I'm using a binary search tree, what do I care if duplicates are to the left or to the right, right? Maybe in some visualization I can see that they're to the left or to the right. But overall, in terms of the functionality, that's internal functionality issues, right? So count, what do? It's just a binary search. Except here, comparison, so 1, okay, if we ever get to null, 0. Otherwise, if we find it, it's 1 plus continue looking down the right subtree. If we don't find it, and it's less and greater than, it should be to the left. So return the count of the left. Otherwise, count to the right. Maybe I should have said 0 plus count. I don't know. But to make it more self-explanatory, that maybe you would find that easier. I don't know. But like, would this work? Well, let's go. Let's count 5s, right? Let's count 17s actually first, and then let's count 5s. So, is this what I'm looking? No? Okay, carry on to the right. Is this a 17? Yeah, it is. Carry on to the right. Oh, it's null. Return 0. So 0 plus 1 plus 0, okay, or 0 plus 1 plus just return the 1, and we're good to go. Perfect. Let's look for 5. No. 1 plus, no. 1 plus 1 plus 1 plus 0. So 0 plus 1 plus 1 plus 1 plus, well, just return plus 1, plus, you know, there we go. That's how it would work. Cool? Cool. Yeah?
Does the 6 return anything? Or is it just...
The 6 just relays the fact that, like, when we went up to, like, okay, 0 plus 1 plus 1 plus 1. So at this point, it's like a 3. A 3 gets returned from here, and then it goes back up to the search on the left, which just immediately returns the 3, right? It returns the result of calling that count. So it's not adding anything to it, it's just relaying it. Where this one is taking what we got, adding 1 to it, and then giving it up. And then if we ever get to the bottom, it's just 0. All right, and that's that. Any questions? There's our linked binary search tree. Cool. Sorting. Have you ever sorted anything in your life? No? Never?
My room is horribly short.
Yeah, fair enough. Sorting. Now, sorting is a classic toy problem. And when I say toy problem, I don't mean trivial. I mean, it is a perfect problem that we like to look at when learning programming and problem solving. Now, I really should emphasize, really we're learning problem solving and then we're like implementing our solutions via programming, right? So don't get it too twisted that like computer science is programming. No, absolutely not. That's usually how we're like implementing programmatically our solutions, but really the computer science is that underlying problem solving. That's the skill we want you to develop. And that problem solving is a combination of like looking at a problem, understanding a problem, breaking that problem down, maybe breaking it down more, solving the little parts, those little problems, and then building and building back up, right? That's the big thing. That's always why I'm saying, like on your assignments, implementing your assignment is like the last thing you do. Obviously, I get that it's a bit of like it's a cyclical process. It's an iterative process. But really, there's no sense implementing a solution before you have a solution. Common problem new programmers have is they sit down and they're like, uh-oh, now what? I don't know how to solve the problem. How am I going to code it? That's the assignment, right? Like that, they don't see that, right? That process of problem solving, it's not about giving me an answer. It's about getting an answer. That's the point. So sorting, like searching, is an easy to understand problem. But it's an interesting problem. It's well understood, so if I say sort something, you know what that means, okay? But it turns out it's actually kind of tricky. Like, you've sorted things before, so I know you're familiar with the problem, but how much have you really thought about sorting? Probably not much. Have you thought, what are the processes I followed to sort these things? I don't know, but I ended up with a collection of blocks sorted alphabetically or something, right? Like, you're doing it, but you might not really be aware of how you're doing it. And you've probably never thought of the computational complexity of what you've been doing. Turns out there's a lot of sorting algorithms. Some work in very similar ways, and some work in very different ways. Some are better than others sometimes. Some are better than others all the time. Some are absolute garbage. Yeah. So sorting is actually really interesting. And it turns out that, like, you might say sorting. Well, how many millennia have people been sorting things, right? Probably a lot, right? Cavemen were sorting their clubs by size. Who knows, right? Like, they were sorting things. But it turns out that, now, maybe in the past, people have sorted things in a really clever way. But it turns out it wasn't until not that long ago before we came up with better sorting algorithms. Or at least they were like formalized. Turns out, like, it seems like we've been sorting things terribly for millennia. Which is wild to think about, that, like, really, sorting, isn't that a solved problem? Well, anyways. So, by the way, a lot of the images that I'm about to show you I've just taken directly from Wikipedia. You may have seen some of these before. If you click on the image, it will take you to the respective Wikipedia page if you want to learn more in the history of bubble sort or whatever, right? So, given a collection of things, and these things can be anything that we might want to sort based on some ordering, right? Like, think of like a binary search tree, right? We couldn't put things into the binary search tree if they didn't have a defined ordering. As long as I have a defined ordering, though, I can sort them. Like, I can sort numbers. And chances are, if I say sort these numbers, you know what I mean when I say sort them, right? Every once in a while on a test, like, I'll be like, add these numbers such that they're sorted, such that they're sorted or something. And some student will always ask, do you mean like increasing? And it's like, yes, of course I mean increasing. Fair enough, but, like, obviously we know what I mean. Strings, right? Sort these strings. If I tell you sort these strings, though, what are you probably going to do? Read them, yeah, and like sort them like alphabetically or lexicographically or whatever you want to call it, yeah. If I say sort these people, how are you going to do it? Height, age, eye color. How do you sort those?
I don't know.
Okay.
You can have more than one group. Just if your eyes blue, go over there.
You compare what?
So you got to figure out what you're comparing them by first.
Well, that's, yeah, so what's the ordering, right? That's the question. Well, anyways, whatever. If I say sort these car parts, what do you sort them by? By what they are?
Yeah.
Their price, their model number, their mass. How annoying it was, sure. The point is, we can sort anything as long as we have a defined ordering for it. That's what that, like, comparable thing was, right? But the same thing goes here for sorting. So if I say, here is a collection of things with some defined ordering, and I'm going to use numbers because it's pretty natural for us. The goal is to arrange the collection of things such that they are in order. Okay? Now, to be clear, if I say sort the numbers like 1, 5, and 7, well, you can say like 1, 5, that's not a 5, 1, 5, 7, right? Like, okay, they're sorted. I don't need to have like 1, 2, 3, 4, 5, 6, 7. Like, I don't have to have all the numbers. They just need to be in order. I can give you the numbers like 1, 2, 111, and 1 million. No, I can't do that. That'll be confusing. 1, 2, 3, 4, 5, 6, 7, right? Like, whatever, right? Like, okay, they're sorted. I don't have all the numbers between 1 and 1,234,567, but that's fine. They are sorted. If I give you the number 1, oh, that's sorted, right? And nothing's out of order, at least, right? I know it kind of feels kind of silly, but it is, right?
You could also give me
You can give me nothing. I'm going to give you a list of numbers and sort them. Okay, here's the list. Done. Wow, you're done already. Wow, that was fast, right? Like, nothing's out of order. They're all there, right? So that's kind of an interesting like peculiarity. Lists that are empty are sorted, and lists with one element in it are sorted by definition, which feels like a little bit of like a little cheesy thing, but you know, it's true. But that will come back in a moment. Now, order, what in order mean, yeah.
Is it possible to have a non-linear, like, ordering system?
Not in a linear system. You mean like, well, you could think of,
There's still linear order.
you could, do you mean like what to do with like the priority queue? If things have like the same priority. And it's like, okay, well, if they have the same priority, like how do you break ties? Do you mean like cases of like how do you break ties? Because you can sort things and like do separate indexing, right?
I guess it's sort of like, hey, what comes after this? Could be this or this.
Well, we're worried about linear orderings right now. So we'll go with this. So what order means really does depend on the collection of things. The things themselves kind of like have to define their ordering, or there must be an ordering defined for those things. Like with numbers, Java uses the natural ordering. This ordering is referred to as the class's natural ordering, and the class's compared to method is referred to as its natural comparison method, whatever. Basically, okay, numbers aren't ordered. They're ordinals, they have numbers. Strings could be sorted alphabetically, but you know, we could sort by length if we wanted. But you know, usually people are going to think like alphabetically. We could sort people based on height or age or month and day of birthday. You know, we could do whatever ordering we want. We could car parts by mass, production code, date they were made, their volume, the amount of dust particles on the surface, whatever we want. As long as we define an ordering, there's an ordering. But with numbers, there's no need to ask, because it would be like if I say sort these numbers, everyone probably assumes like, okay, in increasing order, right? I would probably, like, if I were to say sort these numbers and then on the test later mark everyone wrong and be like, I meant in reverse order, I'd be an asshole, right? Like, that's ridiculous. All right, so, but with other things, we need to have the ordering defined for those things. The things themselves have the orderedness for them. The orderedness has already been discussed a few times, like comparable. More complex orderings can be defined, though, like with the comparator, which you've all used on the assignment 4, right? So, yeah, which was due on Monday, right? You all finished it? Yeah? Did anyone decode the name of the assignment? I must have changed something, because no one could, just, unless it was like nothing, 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 L, comma, M or something. Yeah, that's not right. Anyways, I don't know. Maybe I've changed something and it can't be decoded anymore and it's lost to oblivion because I don't remember what it is. Anyways. For ease, numbers will be used for all the sorting examples we have here. Okay, why? Because we know what they are. Like, we could say we'll sort them in monotonically increasing order, which is an obnoxiously mathematical way of saying just like that, okay? They don't need to go up the same amount every time, and they are never going to be like decreasing. Should this be monotonically non-decreasing order?
Oh.
I guess monotonically that could be the difference, because they were whatever. It doesn't matter. Long story, in order, okay? And ties, oh, if I want to put an 8, should it go here, 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 here? It doesn't matter. It doesn't matter, okay? Cool. So any questions about what I mean by sorting numbers? No? Okay. So here's a fun idea. Yes? What are numbers? You know what? That's outside the scope of this course. So you should either go ask a grade 1 teacher or a math professor. Nowhere in between, and you will get vastly different answers. Okay? All right. Okay, so here's a fun idea. So given a function is sorted. What it is, I don't care about what it really is underneath, but we've got this function is sorted that returns true if the collection is sorted. Yeah?
So for the record, monotonically increasing is fine.
It's fine? Okay. So it doesn't have to be monotonically non-decreasing. Okay. Thank you for checking. What would this function realistically look like? Well, basically it's a linear search that goes like, is every number not less than the number that came before it? If that's true, it's sorted. Okay? Basically, if I were to go through this and be like, is this number less than this number? No. How about that? No, 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 and we're fine. If we ever get a number where the one on the right is less than the one on the left, the whole thing's a mess. It's not sorted, obviously, right? Yeah. And by the way, if you're like, well, that only compares the two next to each other. Yes, but if this number is not less than this number, and this number is not less than this number, then I know that this number is not less than that number, right? So it's okay, we're fine. All right, so given this function is sorted, it's a linear time function. It's just a linear search to go through. Is everything fine? Yep, just this little scan of, okay, good. It'll tell me in linear time, is it sorted or not? And given another function called shuffle, randomly shuffles a collection. Think like shuffling a deck of cards, okay? That's going to be linear time. There's a fancy shuffle algorithm. I can't remember what you call it right now, but okay, 2 linear time algorithms. We could do an algorithm that looks like this for sorting. Now, it's rather silly, perhaps, but while not is sorted, shuffle. What this basically means is take your deck of cards and shuffle. Are they sorted? If they are, you're done. If they're not, shuffle them again. Are they sorted? And so on and so on and so on and so on. Now, what's the best case scenario with this? Well, the best case scenario is, well, it's linear, right? Like, you only need to like shuffle once. Maybe you don't even need to shuffle. You just check. Is it sorted? Hey, it's sorted. You're done. Hey, awesome. Worst case is, I guess, forever. Because I guess it's possible that you shuffle a deck of cards and then you shuffle it and you get the exact same ordering, which would be insane, but you know, it's possible. So yeah, so like if you try to think like how many permutations are there of 52 cards? Well, how long would it take to go through each of them? Well, the problem with that is like we'd have to play some like probability game, and like if I were to shuffle, like if there's like how many of 52 cards are there? So let's yeah. Okay, so about that many. Okay? Right, so that many, right? Yeah?
So does this mean computational complexity is n factorial?
No, it's worse.
Yeah, worse.
And here's why it's worse. Because if I were to shuffle the deck, let me put it this way. If I were to shuffle the deck that many times, does that mean I would get every permutation?
That would be extremely unlikely.
No, meaning like it's definitely at least worse than n factorial.
Yeah.
So really, we could get really unlucky and do this that many times and get the exact same permutation every time. Now that would never happen, but it could maybe, right? So anyways, the point is, this is a terrible sorting algorithm. But you know, it's always kind of fun to start with a really silly one. So the reality is though, like if you were to do this with a small n, it'll do it, right? You hit run, it'll probably take a few seconds, but it'll do it, right? It'll work. Every time you hit run, it might take a little bit varying amount of time, right? Because it's random, but you know, it'll work. But it doesn't take long for that n to become a bit of a problem, like 52 cards. There's 8 times 10 to the 67. I guess there's 67 zeros there, right? That's a big number, right? And to put that in perspective, there are roughly 2.4, that times is wrong, I need to fix that. times 10 to the 67 atoms in the Milky Way. So if assuming ordering to individual atoms in the Milky Way, there would be roughly, is that right? How many? Yeah, okay. Yeah, I have it worded right. I don't know why I got confused. Point being, I would have 5.7 times 10 to the 67 orderings left over, right? Like if you take every atom in the Milky Way, we're running out of atoms and we still got a lot of orderings left. Yeah.
How is this true if there's only 1,082 atoms?
Yeah, I don't know. You're right. Yeah. This is what this should look like, that x. That x is wrong. It needs to be a slash times, not an x. So my mistake there. I can fix that later. You're doing it right. Perfect. Thank you. In the two places. So just do space slash times space and it'll be good. Let's start with bubble sort. Have a look at it. See if you can figure out what it's doing. Now, is it done? No. A lot of people mix this up. There, that's bubble sort. So what is it doing? Well, clearly, it's looking at adjacent pairs, and if they're in order, they're left alone. If they're out of order, you swap them. But doing one pass, you're not done. Clearly, we can see that. Now, most of the time I ask students, describe to me a sorting algorithm you do. A lot of people will describe bubble sort, but they'll only ever describe one pass, and they, for some reason, think it'll work after one pass. Of course, it doesn't. Yeah? After one pass, let me refresh. Notice, if we follow that rule, what must be true after one pass? Because imagine the worst case, 8 was here. Is it out of order? Yeah. Is it out of order? And it would go all the way to the top. That's the bubbling, okay? That's the name, the bubbling. The numbers bubble on up to where they belong. So after one pass, the biggest number is there. After two passes, the top two biggest numbers are there. If I have n numbers, how many passes must I do? N minus 1, I guess, because once this one's in the right place, this one must be in the right place. But let's say it's like n, right? Yeah. Now, how long do you think it takes to do one pass? N, linear. And if I have to do a linear thing, n times n squared. So first of all, we just like intuited why it must be n squared, okay? Now, obviously our analysis there wasn't very formal, but I'll tell you it's correct, okay? And we could also think like, okay, for the first pass, I'll do n things. Then I have to do another pass, right? But that's true. That's a good point. After one pass, like look, watch, perfect. Perfect timing. Look at this. Okay, so there we go. Okay, 8's in the right place. Perfect. Let's do another pass. But I know 8's in the right place. So I go, swap, swap. I don't need to compare the last two anymore, actually, do I? Because I know 8's in the right place. So really, I only need to do n minus 1, n minus 2, n minus 3, and then like 2, 1, whatever. And you look at this and you're like, it's a square, but it's actually about half a square. but 1/2 n squared, who cares, right? So like we can visually and like geometrically kind of like visualize, okay, square, right? Right? It's possible we have sorting algorithms that maybe we don't get this like n minus 1, n minus 2, like it's n times. You really do get the full square, n squared. Another way we can think of that arithmetic series that I know we've been over several times before. This marker's losing its pop. Right? First time, I've got n units of work. The next time, n minus 1, n minus 2, plus like 2 plus 1, right? Right? You recognize this? It's in reverse though. 1 plus 2 plus 3, right? It's the arithmetic series. You remember it's like 1/2, what is it? 1/2. Oh, sure, you know what? I can't remember what it is, but don't worry. It's easy to remember what it is, right? Because what was the trick to coming up with that little formula? Is you double the series by going like this. Let's just write it again backwards. Oops, 1 plus 2 plus 3 plus. That's a plus. I don't, what? There, that solves it, I guess. N minus 1 plus n, right? But I doubled it. So if I doubled it, I have to like undo my doubling later. Ignore this. Let me grab my eraser. And like, oh my gosh, it's n plus 1, n plus 1. If I add all these numbers, it's n plus 1, n plus 1. So I have like an n plus 1 plus n plus 1 plus n plus 1 plus n plus 1 plus n plus 1. Look at that. I've got so many n plus 1s. Actually, how many n plus 1s do I have? N. Why? Well, 1, 2, 3. Yeah, I have n plus 1. But I doubled it, so I have to undo that. Right? Put some brackets? Where? Oh, I see what you mean, yeah. Which, of course, if you multiply that out, okay, we got like 1/2 n squared plus n. And then, oh, well, no one cares about this crap. Oh my gosh, it's n squared. There we go, right? So that's our quick and dirty. So there's a lot of ways we can derive this, but we haven't even looked at the code yet. We're just thinking about the algorithm, and we're already able to kind of get a sense of its computational complexity. So bubble sort, whatever. We just went through it, fine. What's the worst case scenario? Well, the worst case scenario, because like, okay, first of all, let's acknowledge that like, imagine I gave you a list of numbers in order, right? And I start doing this. Like, let's say I gave you the numbers. Of course, no, we're good. One, 2, 3, 4, 5, 6, 7, 8, right? Now I know I need to do n passes to guarantee I'm done. Let's do one pass. Are they out of order? Are they out of order? Are they out of order?
No.
Are they out of order?
No.
Are out of order? Out of order? Out of order? Okay. So I did one pass and nothing was out of order. But I have to do n passes to guarantee it's done, right?
No.
No. Because what I could say is if I ever complete a pass and nothing swapped, I know that we're good. Now, if, for example, I have like a 6 and a 5, and I'm going through, oh, something's out of order. Right? I got to swap right? As soon as I do one swap and I get to the end, I can't guarantee, I know like in this case, like, oh, it's done. But like I could have had like, right? Like if I do one swap, you're like, well, if only one thing was out of order, then clearly it's safe, right? Clearly if I go through a pass and nothing's out of order, I'm done. If I go through a pass and one thing was out of order, but I fix it, I'm done. But you don't know if that one swap you did actually fixes it. Because I go out of order, out of order, out of order. Ah, yes. Okay, let's fix it. Only there, but out of order, out of order, out of order. Oh, I must be good. No. Because clearly it's not, right? These 3 and 4. So even though I did one swap, just because one swap fixed one thing, it didn't mean it fixed everything that was like out of order. So we can only really know if we can stop early if we do a full pass and everything was in order. No swaps, we're done. Yeah?
Would you also be able to implement something that could work even if there were things out of orders where like from the last spot that you swapped, everything afterwards is fine as long as there's nothing else you swap after that?
As you could start to add more logic in there if you really wanted, yeah.
That would be a good thing to do recursively, I feel like.
So, well, let's keep something like that in mind. So, now here I'm talking worst case scenario. So like best case scenario is if you give me something that's already sorted, then I only need to do one pass. And this sorting algorithm could take linear time. But whenever we're talking about computational complexity, we're always worried about the worst case scenario actually. Meaning, okay, so linear time is best case scenario, but what's worst case scenario? Well, I know that it's like n, like we already know it's n squared, but like what would be the state of the, because like that n squared is like an upper bound, but like what actually is the worst case scenario?
First element at the end.
The first element's at the end. It's worse than that because if everything was like out of order, I guess it's still only if the thing, the first thing is at the end. Like if it's like this.
Yeah, because you still got to do it.
1, 2,
First thing at the end.
Yeah.
3, 4, 5, and then we have a 1. Yeah. So we would have to do one pass. Yeah, you're right. So worst case scenario, how many passes? After a single pass, the largest n passes is sorted. Best case scenario algorithm. Oh, do I not actually go into like what the worst case is? The list is in reverse order. That's actually, yeah, you're right. We could actually be more precise. It's actually more nuanced than that. It's actually, if the last thing is, yeah. Very good point. Best case scenario, already talked about it. So what's the algorithm? Well, here's the algorithm. Well, the list is not sorted. For each pair, adjacent pairs, if they're out of order, swap them. And then remember if we did a swap or not. That's it. That's the algorithm. Repeat. Right? Note that the list is not yet known to be sorted. There we go. Computation, we already did that. Cool. You like that algorithm? It's a fun algorithm. Obviously it's not Java, but that's the algorithm. You could implement that. Cool. Let's do an activity. Write for me what the, give me a workable is sorted method. Assume collection is like an array of integers for simplicity. So you can like index it. Pardon?
So literally just sorted and not like sorted?
No, don't, just write the code to check if an array's elements are sorted. Don't sort it, check if it is sorted.
And assume they're integers.
And assume they're integers for ease, yeah.